here to this nice and cool place. I'm going to talk about three different things in this talk. When you go to an Italian restaurant and you look undecided about the choice of the first course, the waiter will often tell you, possiamo offrirvi un tris di assaggini. And then you will receive a plate with three different items, three different first courses in small amounts. And I typically don't do that. I don't like that. I prefer one big plate with one thing. But today my talk is going to be three things. The first is a continuation of what John was saying, high derivative gravity. Second would be about metric-affine gravity. And the third would be something about a cosmological constant problem. So to continue, this is based on this recent work with John and Diego, who's sitting there, and Gabriel Menezes, who was a former student of John's. This is my notation for the couplings of high derivative gravity. The c-square term has a 1 over lambda coupling, and the r-square term has a psi coupling. This theory is renormalizable. It propagates a massless graviton, a massive spin 2 ghost. Then there's going to be some discussion whether one can get around this ghost problem. And then there's also tachyons. So in the lambda psi plane, if psi is positive, the spin 0, the massive spin 0 particle is a tachyon. And if lambda is negative, the massive spin 2 particle is a tachyon. So either on the left side, so both on the left side of this plane and in the upper half of the plane, you have tachyons. The only tachyon-free part is that fourth quadrant. So please remember that because it plays a role in the following. So we want to talk about the beta functions of this theory. And you have to use a background field method. So you expand the metric into a background G bar and fluctuation field H. And you will find that when you linearize, the field H, the quantum field, propagates according to an operator that looks like that. Is a pointer? So you have a covariant box bar squared. It's the covariant Laplacian in the matrix G bar. And then you have terms with, you can get rid of the three derivative terms, and you have terms with 2, 1, or no derivatives. So you can arrive at this form by choosing the gauge and choosing the normalization of the fields. And then you will find that this V part contains the background curvature, and N contains the covariant derivatives of the background curvature, and U contains either Laplacian of the background curvature or background curvature squared. In normal two-derivative theories, O has dimension 2, and then the field U is linear in R, but here it is quadratic in R. This plays some role in our discussion. So how do you use the background field method? There are various ways of doing that. One is to choose a particular background, like a sphere, and do the calculation there. And in that way, we could compute, for example, the beta function of psi, the R square term, but we could not compute the beta function of lambda because while curvature vanishes for the sphere. So you need more general backgrounds, and you can either do the calculation by computing, by choosing a background that is a small perturbation of flat space, or perhaps even better, you can choose an arbitrary background. Now, historically, the second method was used by Jules-Vetonin in the first attempt at working out the beta functions of high derivative gravity. But their calculation contained some mistake because they were missing some pieces. And then the correct calculation was done later by Barvinsky. That was 1985. And they used a generic background. And since then, everybody has been using that method. This beta function comes from the fourth heat kernel coefficient. Before that, for the operator that I showed, this heat kernel coefficient has the form shown here. It contains, you see, the square of v, and is linear in U. When you have an ordinary theories with two derivatives, kinetic terms, this you will have here U squared, but now you have U. And again, U contains R squared. So this contributes to the beta function. And the beta functions are written here. They've been well established. So this is beta of lambda. Omega is the ratio of psi over lambda over psi, actually. And this has to do with the Euler term, which we can ignore because it's a total derivative. Well, so these beta functions then have been confirmed by several other people in various calculations, including calculation based on the functional renormalization group in various approximations. Now, the question is this the physical running? What do we mean by the physical running? In particle physics, the beta functions are used to gain some information about the behavior of the theory or the scaling of scattering amplitudes with energy. And basically, this is what John was writing down here. So you want the behavior of the beta function. You want the running coupling to run in a way that reflects the behavior of the amplitude with energy. And so the best way to do the calculation then is to use the second method of the one that was used originally by Ulvetonin, and use a background G as G bar plus H, and next we are going to write G bar as flat metric plus H bar. So the quantum field is really H, and H bar is the background, basically. It's a fluctuation of a background. It's a bit of an oxymoron, perhaps, but the background is just a flat plus some field H bar. So when you do that, then the operator becomes the flat Laplacian, and then terms with 4, 3, 2, and 1, and 0 derivatives. Now, ordinary derivatives now. And these coefficients D, C, V, N, and U are power series in this field H bar. Remember that all contain the covariant Laplacian. Now the covariant Laplacian contains Christoffel symbols of the covariant of the background metric. And when you expand those, it will give rise to terms that contains these H bar and derivatives of H bar. Okay, so then you have to do you can compute the running from the 2-point function. So here you have the thick lines are the background, the propagators of H bar, and the thin lines are the propagator of the quantum field H. So this 2-point function would be a function of this external momentum P, and at one loop, you just have this bubble and a tadpole contribution. And now you can ask yourself how these bubble and tadpole contribute to the beta functions that are known in the literature. And in particular, how they enter in this B4 coefficient. And you see what happens here is that notice, for example, the following fact, that here U appears linearly. Now, if you look at this operator, U is if you look at this operator and these diagrams, these vertices are all linear in these objects D, C, V, N, and U. And from the fact that U appears in the beta function linearly, you conclude that it must come from just a single vertex. So that is a contribution that comes from the tadpole. And as John said earlier, the tadpole does not depend on momentum. And so this particular contribution to the beta function has nothing to do with the energy dependence of the two-point function. And so in some sense, it is unphysical. So this was the first hint that there is something strange going on with these beta functions that are known for a long time. And then the point is just to compute the what we call the physical ones. Now, perhaps I have the slide here that may help to clarify. This is very similar to what John has already written there. If you suppose you have an amplitude, a hypothetical amplitude, that is a function of the external momentum P, where you have the tree-level term is some coupling lambda, and then you have quantum contributions. Now, in typical textbook cases, the only thing that you see is this middle term. You have log of the p square over mu square. But in theories, like where you have a mass, like John was saying, there can be further terms, like this log of m square over mu square or log of p square over m squared. So in particular, in these calculations, this first term comes from the tadpole, and the other two come from the bubble. And this one is related to the high energy part of the bubble, and this one is related to the infrared part contribution to the bubble. And so yeah, but here we're more general. Okay. Yeah. Sorry. Yeah, of course you can do it that way, and then it doesn't enter. Yeah, but now if you look at this and you use the standard definition of the running coupling, namely you impose that the amplitude is independent of mu, it will give you the beta function for mu that is 2a plus b lambda squared. It comes from these two terms, you see. But you see, this term has nothing to do with the momentum dependence. On the other hand, there is a term here that is momentum dependent, but it doesn't depend on mu, and so it is not captured by the mu dependence. So there's a difference between this that we call the mu running and what is actually the momentum dependence of the amplitude, which is contained in these two logarithms. So, yeah, mu is unphysical. I agree. Yeah, indeed. Indeed, the beta function comes from the assumption that the amplitude is independent of mu. Anyway, you can at this point rewrite this. This log of p square over m square, you see, you can say that this is a log of p square over mu square, and you add it to this term, and then you plus the logarithm of, or rather minus the logarithm of m square over mu square, and you add that piece here. And then this becomes this expression where you have here all the momentum dependence just in one term. And this term now, you can, if you wish, you can absorb it in the definition of the renormalized coupling. You can say that the renormalized coupling is not just this, but this plus the log, this log. And then you get the formula for the amplitude in terms of this new renormalized coupling, which is like that, and it is of the standard type. Now, if you take the derivative with respect to mu of this, you get a different beta function. It is 2 times b plus c. You see, previously it was a plus b. And that's not the physical beta function. the physical beta function is 2 times b plus c. And indeed, you see that the dependence, if you take derivative with respect to mu of this, it does give you b plus c. And it's the same as if when you take the derivative with respect to p, it gets the same coefficient. So this beta function correctly reproduces the momentum dependence of the amplitude. So this is what we mean by physical beta function versus beta function that we would compute by blindly taking derivative with respect to mu. Okay.
Now, you were doing this in terms of subscale mu r at which you renormalize and reabsorb.
Yes. Okay, so you do this now you do the calculation. Now there's one more thing that I should say is that in this high derivative gravity calculation, the coefficients A, C, and B by themselves in the perturbative calculation are not covariant. But if you take the sum B plus C or the other one, A plus B, those are actually covariant terms. So if you take mu d by d mu, you get this A plus B beta function, and you will reproduce exactly the old beta function of Avramidi-Barvinsky, the one that is known in the literature. And it's covariant, and it has all the nice but it is not. It doesn't reflect the momentum dependence of the scattering amplitude in the theory. This B plus C, you do the calculation, it turns out to be, again, covariant, which was, I think, this is the strongest test that we have of our result. And so this is now the new beta functions that are written here on the right. You see that they are quite similar to the old ones, except that coefficients have changed somehow. But this change in the coefficients has some relevance because asymptotic freedom happens in this yellow region. For the old beta function, the asymptotically free region is the first quadrant minus this thin wedge that you see here. But it is very thin here, but it's minus a thin wedge. And this region, you still had a tachyon, remember? The spin zero, the massive spin zero particle is a tachyon here. So you can have, with the old beta function, you can have asymptotic freedom at the price of having a tachyon in the theory. But with the new beta functions, the region of asymptotic freedom is the first quadrant plus a thin wedge in the fourth quadrant. And the fourth quadrant is free of tachyons. And so this is the main novelty of this result. And I think it's a little step forward in the sense that it makes it's a step towards making this theory a little bit more acceptable. It still had problems, but at least this problem of the tachyon at least is not there anymore. Okay, so this was the first part of my talk, and perhaps I can divide my 10 minutes of questions into 3 times 3 minutes and 20 seconds of questions. So please, if you have questions now about this. All right. So I continue. The second topic was metric-affine gravity. So let me start from this effective field theory that John talked about, which is based very much on the analogy with the chiral theory of strong interactions at low energy. So there is a very strong similarity. The chiral field at low energy is the exponential of the pion field divided by some mass parameter, which is the pion decay constant. And now in gravity, we can parameterize the metric as the exponential of the graviton field divided by the natural mass scale of gravity, which is the Planck mass. Previously, I wrote that the metric is the background plus a fluctuation, but you can also parameterize it in this exponential way. It's better for the purpose of this analogy. And then the first terms in the expansion of the chiral action are the linear in quadratic in u minus 1 du, or fourth order in u minus 1 du. This quadratic piece has a dimensionful coefficient f pi squared, and the other ones have dimensionless coefficients. And similarly in gravity, you have the term linear in R with the Planck mass squared, and then R squared terms which have dimensionless coefficients. And now if you remember that the curvature contains two Christoffel symbols, and the Christoffel symbol itself is the inverse of the metric times the derivative of the metric. You see that all these terms, this term looks very much like u minus 1 du squared, and these go like u minus 1 du or g minus 1 dg to the power 4. So it's very similar. The main difference is the fact that in gravity you have the square root of g there, with the effect that a constant term in the Lagrangian, the cosmological constant, actually is physically important. I mean, it depends on the field. But if you do unimodular gravity, even that goes away because G is 1 then. Anyway, so this is a similarity that the metric theory of gravity as an effective field theory is very much very similar to the theory of strong interactions. And I want to stress instead similarity with electroweak interactions. And I want to talk about metric-affine gravity, which is a theory where you have independent metric and connection. Now, why should one emphasize the connection? Because the connection is the one thing that gravity has in common with the other interactions. All the other interactions that we know are gauge theories. The main dynamical variable is the connection. In gravity, we do have a connection, but it's a bit it's not dynamical usually. So I want to talk about theories with dynamical connection. And my notation is that the independent connection I call A, the covariant derivative I call D, and its curvature I call F. And the Levi-Civita connection instead, which is constructed out of the metric, I call gamma, the covariant derivative nabla, and the curvature is the Riemann tensor. So this is typical GR notation, and for the independent connection, I use this Yang-Mills type notation. Okay. So in addition to curvature, you have new geometric objects, which are the torsion and non-metricity. And if you work in a generic frame, the torsion is the covariant exterior derivative of the frame, and the non-metricity is the covariant derivative of the metric. So as a theory of the metric and connection, you can write the action, and it's going to be an integral of powers of torsion, non-metricity, curvature, and d-covariant derivatives. So I call this Cartan way of looking at the theory. The variables are A and G, and this is the action. But when you have an independent connection A, you also have always the Levi-Civita connection because the metric is there and you can construct the Levi-Civita from it. And the difference of A minus gamma is a tensor phi. And this tensor itself is a linear object in torsion and non-metricity. And so any action for G and A can be rewritten as an action for G and phi, or equivalently G, torsion, and non-metricity, where in this case torsion and non-metricity have to be thought of as independent fields. And so this is just a field redefinition. So you have this new action that will contain, it will be constructed with torsion, non-metricity, the Riemann tensor, and Levi-Civita covariant derivatives. So I call this the Einstein way of presenting metric-affine gravity because it looks like metric gravity plus some fields, T and Q. Okay. And incidentally, if you want to do any calculations in this theory, it's always much easier to work with this Einstein presentation. So let's think of this as an effective field theory. So we have to order the terms in the Lagrangian according to their dimension. And the terms in the first line are of dimension 2. It's either linear in the curvature or linear in torsion and non-metricity. T and Q have dimension 1. So T square and Q square are mass 2, dimension 2 terms. And the other two lines are dimension 4 terms instead. And so you see you can have terms quadratic in curvature or quadratic in the derivative of phi, or mixed terms f d phi. So these terms are quadratic in f and phi. And in the fourth line, you also have dimension 4 terms that are cubic in f and phi. So either f phi phi or phi phi d phi or 4 phi's. Okay, so this is the expansion of this theory at dimension 4. So it's somewhat similar to the one that I showed earlier for metric gravity, but it contains many, many more terms. If you work in a completely general metric-affine gravity that, with independent metric connection and so on, and torsion and non-metricity, there will be of order 1,000 terms if you include all of them. It's really awful. Now, if you keep only the dimension 2 terms, which are the leading ones at low energy, you know what happens, because that Lagrangian is basically the Palatini Lagrangian. The equation of motion will tell you that torsion and non-metricity are 0 in pure gravity. If there is matter, it's more interesting because you can have non-zero torsion then. But torsion and non-metricity are non-dynamical objects, basically. On the other hand, if you include dimension 4 terms, then T and Q become propagating fields. But they are massive. And the interesting thing here is that the mass of these objects you can see as coming from a sort of Higgs phenomenon. Now, the essence of the Higgs phenomenon in a gauge theory is the following. You have some, you have a connection field, gauge field, and scalars. And among the scalar degrees of freedom, there are Goldstone bosons. And the essence of the Higgs phenomenon is that kinetic term of the Goldstone bosons is just a gauge invariant way of writing a mass term for the connection. Now, in the case of metric-affine gravity, the metric field and or the frame field play the role of the Goldstone bosons. Let me define a Goldstone boson to be a field with values in a coset space. If you think for a moment, you will see that this is completely a reasonable definition. Now, the metric is a field. The metric and the frame you think of it usually as linear objects, but they are not linear objects because there are constraints on them. And the metric is a field with values in the coset GL4 divided by the Lorentz group. And the frame is an object that has values in the linear group. So those are nonlinear objects, and they carry nonlinear representations of the linear group. And so they are Goldstone bosons. Torsion and non-metricity, remember I showed you, are the covariant derivatives of these Goldstone bosons. So the terms T square and Q square are essentially the kinetic terms of the Goldstone bosons. And in the Cartan way of looking at the theory, when you expand that around flat space, assuming that flat space is the vacuum of the theory, you will find that these kinetic terms of the Goldstone bosons contain mass terms for the connection. And in the Einstein view, T square and Q square are already presented to you as mass terms for the deviation of A from gamma. Okay, so this means that at low energy, it must be equal to the Levi-Civita connection. So this is very similar to what happens in electroweak theory, when you look at this theory at a scale which is below the mass of the Higgs, because below the mass of the Higgs particle, the radial mode of the Higgs does not propagate, it's frozen. You only have the angular modes that are the electroweak Goldstone bosons. Okay, so you look at the theory below the mass of the Higgs, but above the mass of the W and the Z. And there, the theory will look like basically massive gauge fields. That's all you will see. So massive gauge fields you can either present as the Proctor-Lagrangian, but or as the theory of, or as gauge fields coupled to Goldstone bosons in a gauge invariant way. So this is called sometimes electroweak chiral perturbation theory. Now, what are the scenarios then? Since this connection now is massive, it depends on what the mass, what are the values of this mass. It is somewhat natural, it would be quite natural, that all the masses were of the order of the Planck mass. And in that case, you wouldn't see anything really. The effective field theory of the metric-affine gravity would be indistinguishable from the effective field theory of the metric that John has been talking about. But I would argue that this still has a little bit more explanatory power than just the theory of the metric, because it gives us a dynamical explanation of the reason why at low energy torsion and non-metricity are zero. It explains it rather than being something that you postulate as in textbooks. On the other hand, if the mass matrix of this field phi, or mass matrix of the connection, has some eigenvalues that are smaller than the Planck mass, then there could be new propagating degrees of freedom in the validity, in the domain of validity of this effective field theory. And then there could be very interesting phenomenological applications, and there are people working on these type of topics. Now, suppose that you have some of these propagating degrees of freedom. What do they look like? Sorry, so let me start again. I've been talking of this metric-affine gravity so far as an effective field theory. But if you include the dimension 4 terms, it is, I mean, the couplings have are dimensionless, and then the theory would be power counting renormalizable. It's a little bit like going from Einstein gravity to higher derivative gravity. Once you have the dimension 4 terms, theory could be renormalizable. So is it, you can ask here the same question that you ask about high derivative gravity. Is it renormalizable? Does it have ghosts or tachyons and so on? And so what is known about this is that there are known classes of metric-affine gravities that are ghost and tachyon free. But these subclasses are of measure 0 in the metric-affine gravities. So you have a parameter space that is parameterized by all the couplings in the Lagrangian, and only for special choices of parameters will you have ghost and tachyon freedom. Since there are so many terms, the classification is incomplete. Nobody knows what happens. I mean, nobody has a complete understanding of this, the structure of this. And furthermore, if you are sitting on one of these particular ghost and tachyon free theories, it is very likely that as soon as you include quantum corrections, you will be moved away from that. So very likely these theories behave in a similar way to metric theories, in the sense that if they are renormalizable, there will be ghosts. If there are no ghosts, the theory will be non-renormalizable. I expect that this will be the case. But again, there is no proof. Now, there's precious little that is known about quantum properties of these theories, and there was a calculation done by Oleg Melichev for his thesis of the quantum effect of the one loop divergences in this particular theories where you have just one term proportional linear in f squared and one term linear in torsion squared. And now I just jump to the result. The logarithmic divergences are proportional to this. Now, these LFF terms are quadratic in F. In particular, LFF1 is the term that we started with. This is LFF1. LFF2 will have different contractions, basically. So you have this FF type terms. You start from this, and obviously you generate all the others. And then there are also FT terms that are proportional to FDT and the DT squared terms, and also terms cubic and quartic. There's a lot of stuff. So this is a sample calculation. In particular, it happens here that applying field redefinition to the term T square, you can generate all the terms that I've written in that slide. And so you can absorb all these one loop divergences into field redefinitions. It's a little bit like in pure gravity, where the R squared terms can be reabsorbed by field redefinitions. However, the field equation here is not that R is equal to 0, and so there is one of the R squared terms that survives, and that makes the theory non-renormalizable. This particular one that I looked at. Okay, so there's a whole world there of theories that one could explore that is very little known. And Oleg has also looked at some more general case recently. Okay, so is there any question about this part now? No, very good. You have a question? Yeah, sure. It plays a role in the fact that, in a nasty way, in that, as I said, generically these theories will have ghosts and or tachyons. It's almost a generic property. You can see it for sure. It comes from there, but there are so many ways of contracting the indices. In some cases, it comes from what you said, because if you write Young-Mills Lagrangian with but there are also other ways of contracting indices where things have a different origin. Any other question? Hmm?
Why would one want to look at these?
Well, because as I said, the motivation for me is that this makes gravity similar to the other gauge theories. So this gives, I've written it here, you see? So there's this close similarity with the theories of electroweak interactions in particular. It may contain new propagating particles. I don't know, people say, dark energy. There's a new particle. It could be the dark matter. Sorry, dark matter, not dark energy. It explains the Levi-Civita, why you have Levi-Civita connection at low energy. And it is a pathway towards unification between gravity and the other interactions.
Not sure that is a very
Well, if you open a textbook in GR, you say the connection is the Levi-Civita, and then you may ask why. Children always ask why. And here there's an answer. Yeah.
So when you say low energy, what exactly? What energy?
Oh, much below the Planck scale.
Yeah, but that's very kind of vague definition. So let's say too much low energy somewhere in between present and standard model energy Planck scale. So
Yeah.
exactly
Yeah.
where I can estimate that.
I'm not doing anything. I'm not talking about any specific model with a particular, I don't know, model for dark matter or whatever. But I don't know. It could be anywhere between Guth scale and Fermi scale. Yeah.
One step away from gravity. But there are also poor connection combinations of gravity. So what would be the good choice? What to start with, like one connection?
I don't know. I think Ben has worked on pure connection formulations. I don't have much experience with that. I like these mixed metric-affine because, as I tried to explain, you can see that gravity is a theory which is in a Higgs phase. You know, when you talk about, in particle, in general, in quantum field theory, one of the central questions is what is the status of symmetries? Are they local, global, broken, unbroken, broken by what? Spontaneously, not spontaneously, anomalies, whatever. So knowing that is one of the central features of the theory. And from this point of view, I would say that gravity is described by a theory, by a gauge theory in a Higgs phase. You have the linear group, which is Higgs. So you have a connection for the linear group. It is there. And it's massive. And the mass comes from a Higgs phenomenon. Like in electroweak theory, or like superconductivity. And then you ask, what is the order parameter that drives the symmetry breaking? And in gravity, it is the metric. So I like to think of the metric as the order parameter, a little bit like the Higgs field in electroweak theory, or the chiral condensate in strong interactions, or the BCS condensate in superconductivity. And so from this point of view, I'm inclined to think that the connection may be more fundamental than the metric itself, because in these other examples, the order parameter is not a fundamental field. But okay, this is perhaps more for the discussion sessions. So now briefly, I would like to talk about this last topic, which is related to the cosmological constant. You all know what the problem is. If you compute the vacuum energy of a quantum field, you find, by standard method, you find some quartically divergent result, which seems to imply that space should be very, very highly curved. And the higher the cutoff, the stronger the curvature. So this type of calculation had already been criticized in the past by several authors, but then you just reduce the quartic divergence to a quadratic one. That's already many orders of magnitude, but it still remains a very strong problem. More recently, there was this paper by Becker and Reuter whose criticism is more drastic. They say, if you do this type of calculation, you are basically computing the energy momentum tensor of your quantum field in flat space, but then you find that space has to be highly curved. And so you do a calculation in one space, but the result is another space. So you are way, way off shell in some sense. And they instead try to do the calculation in a different way that I'm going to illustrate. So we are now not doing really quantum gravity, but we are in the context of semi-classical theory, where you have a quantum field, the quantum scalar field in this case, coupled to a dynamical classical metric. So the metric is classical but dynamical. It has an action which is just Einstein-Hilbert with a cosmological term, and the quantum field is scalar field with a mass and quadratic coupling and non-minimal coupling. And since we are just interested in looking at how the universe becomes larger or smaller, depending on the cutoff, it's enough to look at quantum fields on a sphere. So we can fix the metric to be a sphere. The only dynamical degree of freedom of the metric is the radius of the sphere, or equivalently, its curvature, scalar r. So the effective action of the field is just the classical action plus 1/2 trace log of this operator, Laplacian plus mass squared plus lambda phi square plus psi r. And the eigenvalues of the Laplacian on the sphere are known. They are proportional to the curvature times L plus 3. This is a quantum number that starts with 1 and goes to infinity. And they are degenerate, and the degeneracy is this, or multiplicity is this cubic polynomial in L. And so then this trace log is 1/2 sum over L of the multiplicities times the logarithms of the eigenvalue of the Laplacian plus E over mu square. And now, how do we make sense of this trace log? The simplest way is to just stop this sum over L at one particular number n. Okay, so n is essentially the ultraviolet cutoff now, but notice it is a dimensionless number. It's not an energy scale. Okay, so this is a dimensionless cutoff. Of course, if R is fixed, you can convert the dimensionless cutoff n into a dimension full cutoff c squared by just multiplying it with R. You know, if n, capital N, is the largest possible values for L, then the largest possible eigenvalue of the Laplacian is just R over 12 and n plus 3. However, I call the cutoff C because I don't want to call it lambda then, because then it gets confused with the cosmological term. N is independent of the metric. N is a number. The Laplacian depends on the metric. No, I wouldn't say that. Why? The Laplacian depends on the metric. The eigenvalues are these, and L goes 1, 2, 3. I'm putting a cutoff on this, not on this. Lambda depends on R, not L. No, but it's true. What you say is that you do, if R is fixed, you can convert this dimensionless cutoff into a dimension full one. But the point that will appear in a moment is that R is dynamical. So I don't want to treat R as a fixed parameter. What? Okay. Okay. Well, so keep everything fixed and finite. Okay. So then the calculation goes like this. This is the effective action. It's a function of the metric, but as I said, the only degree of freedom of the metric that I kept is the curvature. So I can think of this as a function of the curvature. You have the Einstein-Hilbert action and the trace log. Now, the volume of the sphere goes like 1 over r squared. So the cosmological constant term is something that goes like 1 over r squared. The Hilbert term goes like 1 over r. And the quantum corrections, they go like log r. I split this log of r times LL plus 3 into the first term, log r. Now, this term multiplies the sum of the multiplicities. The sum of the multiplicities I call f. And remember, multiplicities are cubic in L, and so the sum of the multiplicities is fourth order in N. So this is the total number of modes that have been included in the sum. Okay, so this is the first part of the log. Then there is the log of L plus 3. But this is field independent. You see, it doesn't depend on R nor on the scalar field. It's just this constant T. This is this sum here. So for this, but if you consider just a massless minimally coupled theory, this part is field independent. You can forget about. You just consider these three terms: something that goes like 1 over R squared, something that goes like 1 over R, and things that go like log R. You can see here already exactly what happens. The black line is the classical action. So this is when you put the n equal to 0. You have, for small curvature, this is dominated by the cosmological term. It goes like 1 over R squared. And for large curvature, it is dominated by the Hilbert term. It goes like 1 over R, and it's negative. And this has a minimum here at R is equal to 4 lambda. This is the solution of the classical equations of motion. R is 4 lambda. Now you start adding quantum modes. N equal to 1, 2, 3, 4, and so on. So what happens, you already see here exactly what happens. The minimum shifts upwards and a little bit to the left. With each new mode, you go a little bit further left. Okay? Now, further left means smaller r. Contrary to what you normally expect. You expect more modes, more curvature. But no, sir, more modes, less curvature. And if you want to see this quantitatively, you just solve the equation of motion that comes from that action. It's just a simple quadratic equation in R. And the solution is written here in closed form. Then you expand it in n. The leading term is 1 over n squared. Then you have 1 over n cubed, 1 over n4, and higher order. So you see that when the cutoff n goes to infinity, the curvature tends to 0. Now, I'm not saying it is 0. I'm saying tends to 0. This doesn't mean that the renormalized lambda goes to 0, because you see the quantum terms here cannot be interpreted as a renormalization of lambda or of the Einstein-Hilbert term. They are different. They are logarithmic in R. In fact, these are what you would call the anomaly action. If you write the equations of motion, it's the Einstein equation with the expectation value of the energy momentum tensor on the right-hand side. But on the sphere, the only independent equation is the trace. And so you can write this thing on the right as the integral of the trace of the energy momentum tensor divided by the volume. And so the free massless scalar is a scale invariant theory, but T mu is non-zero. It is proportional to f of n. If you compare these equations to this equation here, the right-hand side is f that you can think of as the trace anomaly. Okay. All right. So this was for the free theory. So contrary to what everybody says, when you add more modes to the field, the space tends to become flatter. Now, this is now something new. This is work that I did with Renata Ferrero. Now consider the interacting theory. So the action now, this is the classical action and this is the quantum correction. And so this again, the classical action is terms that go like 1 over R squared, 1 over R, and these are again 1 over R squared. And this non-minimal interaction, it goes like 1 over R again. And for the quantum correction, you can write it again as the total number of modes times log r, plus something that is now more complicated is a function t. And this z now is this term that contains either r and the expectation value of phi. So these are the quantum equations of motion for phi and for r. They involve the function s, which is the derivative of, you see, in the action you have t, so the equations of motion contain the derivative of t, so s is the derivative of t. And it can be expressed as these special functions, they are called harmonic numbers. It's a quadratically divergent function of n, and then there are these harmonic numbers inside. So these equations now are transcendental. You can't solve them anymore. We simplify our lives by assuming that we are in a symmetric phase. So you see in particular, phi equal to 0 is always a solution of the phi equation of motion. So let's assume phi is 0. You can put phi equal to 0 also here. And the equation simplifies a bit, but it's still unsolvable analytically. But you can solve it, we've seen in the non-interacting case that the curvature goes like inverse powers of n. And so let's make an ansatz of this form. And inserting this ansatz into the equation, you can iteratively determine these coefficients k. And these are the first few coefficients. The first one is the same as before, plus m squared, also the cubic one, and psi begins to appear at order 1 over n to the power 4, and also g and so on. Okay. So it is true also in the interacting case that the curvature goes to 0 like 1 over n squared. And now we would like to compute the effective potential. In particular, we want to know what is the effective mass and the effective force quartic interaction in this theory. So the effective mass will you can compute by computing the second derivative of gamma with respect to phi squared. So this will give you the classical terms plus something that comes from the quantum corrections. And the surprising thing is that the quantum corrections are finite. You have to do some calculation with some special functions. You find a finite result, and that doesn't tell you very much, of course. So it is more instructive to do this calculation in 2 steps. In the first step, we assume that we keep r fixed and take n to infinity. And if you do that, indeed there are divergences because the quantum corrections do contain these terms that go like n square, n, and so on, and log n. And then there are terms that I said are finite in the sense that they contain only n to the power 0 or inverse powers of n. So this is the result, and you can read off from here an effective m, and it has this logarithmic divergence, which you can recognize. It's actually the same result that you find in ordinary perturbation theory. You get the log of the cutoff. This gives you a beta function for the mass. And it's the standard result, the standard coefficient. And you also get some running for some divergence for psi effective. But now you have to remember, now an important thing is that we want to go on shell because the field R is supposed to be solve the equations of motion. And I showed you that when you solve the equation of motion, R behaves like 1 over n squared. So you have here a term that goes like 1 over n squared. So this cancels this divergence. This becomes a finite term. This goes to 0. Here you have something that is finite. And here you have something that is that goes to 0 again. So of all these terms that are written here in this bracket, only log n times this 6m square remains. So there seems to be a logarithmic divergence left over out of all these divergences. However, you have to remember that these terms here of order n to the 0 or lower, they also contain r. So you have to look at what their dependence on r. And those terms look like this when you compute them. They contain these polygamma functions of this argument. Now you see the r sitting in here. So when you say that r goes like 1 over n squared, this m squared over r will give you a term that goes like n squared. Under the root, it becomes n. So you have the polygamma of n. For large x, the polygamma of x goes like log x. So you have here log n, and this is also log n. You look at this coefficient here, and it's exactly the same coefficient that appears here. And so what you find is that this log divergence is cancelled by what look like finite terms there. So the result is, as I said earlier, that the quantum correction to the mass is finite. So the effective mass is the mass plus this K2 times log of m squared over K2. This is quite surprising, but I mean, I don't know. You can tell me if you see something wrong in this. And the same thing happens for lambda. Lambda comes by taking the effective lambda comes by taking the fourth derivative of gamma with respect to phi at phi equal to 0. So when you do that, you get the classical lambda, the tree level, plus something that goes like the first derivative of the function s. You have to evaluate this function. It is this sum here. This sum, you see, you have remember that m is cubic in L, and here you have L to the 4 in the denominator. So this sum is logarithmically divergent. It goes like this. And this exactly reproduces the standard. This is the standard divergence with a cutoff. So what I'm saying here is if you treat R as a fixed parameter, you will find a usual divergence here with the right coefficient. But again, there are here some finite terms of order n to the 0, that however depend on R. And if you put R on shell, this dependence on R produces the log n that exactly cancels this log n. Very strange. The result is that the lambda effective is finite. It has just this correction that is proportional to 12m squared over K2. I remind you that K2 was this coefficient here. It's just some function of the parameters that you had in the original Lagrangian. All right, so time is over basically. So that's my summary. And well, I should say that this calculation was Euclidean, and this is perhaps the weakest point of this argument. It would be important to do this in real de Sitter space. Then perhaps you would believe it more. Okay, thanks.
Thanks, Roberto. Okay, time for just one short question. Then we postpone all of the rest to the open discussion. So, John.
Constant. I would think I should be able to add one, make space almost flat, and then you should get the usual divergence.
Well, there was a cosmological term to begin with in the bare action. It is there. It is arbitrary, yes. It enters in this coefficient K2, you see. So you have actually you must have lambda different from 0 in order for this to work. But this particular value of lambda has nothing to do with the curvature that you obtain in the end.
Okay. So since we have 1 hour for
Yeah.
discussion later, let's now thank again Roberto, and we go for the coffee break. So coffee break.